Hello, my name is Artur Schleis. As you might have seen, I have the hoodie, which is in the photo. What's in the photo? That's not me. Do I have a laser pointer here? Yeah, look, there's a hard hat. We're gonna talk about safety. And safety is very important because, we have these delivery models and everything, like in the previous talk. But essentially, it all boils down to one thing. If we deploy something and that something doesn't work, well, somebody's waking up at night, right? So we're going to talk about how we can use the type systems to write safer code that doesn't crash as much, and it's cleaner, which basically means it's easier to understand and it has less tests. Does this work? Yes, it does. Yeah, so what's the context here? This is most useful if, the cost of error is high. So there are systems where, you deploy something crashes, you get some error logs, you hotfix it, that's fine. But as, there are systems where if something crashes, somebody dies, or if something doesn't work, you get millions of damages, then this is probably interesting to you. And one of these examples, like I come from the game development area. So yeah, my day job is to make computer games. I'm a director of engineering at Ultrahorse. And well, you have these huge companies like Apple, Microsoft, Sony, and they have these interesting schedules where you push a build to them and then they take 2 weeks to, review it. And then, you realize, uh-oh, we screwed something up. And then you push another build and they say, yeah, fine, we'll review it in 2 weeks. But no, our game is crashing. I don't know, seems like your problem. So I guess, you being a .NET crowd, you probably don't like dynamic typing, but in general, the idea is that, my background was, and quite interesting one, I came from the dynamic typing, like I started with PHP, Python, Perl, Ruby, etc., etc. And, I kind of liked it a lot, but then, you find out that there's issues with it. There's issues like you can't refactor things because your tooling doesn't really know much about your code. And despite all of your tests, occasionally the type errors still pop out. So it's a problem, and that kind of pushes you into more of a statically typed world. And I guess it's a trend that we see now that, JavaScript's getting TypeScript, and, even PHP has static typing now these days. So this kind of gives us an idea that the more things we can put into the type system, the more reliable our software will be. So how does the static typing help us? Well, that went horrible. Okay, how does static typing help us? Maybe this wouldn't have happened. Probably not. Is this the next slide? Yep. Okay, so yeah, one of the things that static typing help us, it reduces the number of tests. If you have compiler checking for something at the compile time, you don't need to write tests. And we have to agree that tests, they really kind of suck. Like, nobody really likes writing them, right? And if you write a test, then you need to maintain it. And then, if the functionality changes, then you also need to change the test. So, and the best test is a test that does not exist, because then you don't need to write it, you don't need to maintain it, everything's great. So the idea is that you can use the type system to make illegal states irrepresentable, therefore eliminating the need for tests that test whether those states have happened. We can increase the code clarity by using types. So we can use types to communicate not only what something is, like is it a number, is it a string, but also what semantic context does it have? Why is it a number like this? So you can say, this is not, a string, this is maybe a person's first name, or maybe a street name, or maybe something else. So one of the things often that you have is, you have to write comments, and you get some parameters in the code, and they say, what does these parameters do? If you move the comments to the type, you don't have to comment the parameters anymore. So you can actually kind of don't repeat yourself on the documentation for the semantic meaning of the parameters. And we can make sure that certain things that we know that are true, certain invariants are being, enforced at the compiler level through the whole code base. It reduces the amount of it reduces the amount of runtime exceptions. So, runtime exceptions are essentially about, we expected the state to be in this, but it wasn't. We expected this to not be null, but it was, or we expected some other precondition to hold, but it did not, and then we get an exception. If we can eliminate these illegal states, the representation of those states, then we don't have exceptions anymore. And at the end of the day, it just makes everyone happier. It makes developers happier because, we spend a little bit more time writing the code, but when you come back in a year and take a look at the code, you can understand the code much quicker. The types guide you. You don't have to spend as much time figuring out what is going on. And in the long term, the software becomes cheaper because the developers can write reliable software, non-buggy software faster, and they, are happier with your code base. They don't leave as much, etc., etc. So it's good for business as well. So how do we actually do it? And there's a couple of things. We're going to start with the semantic types. So the examples will vary between Scala and C#, but it should be fairly understandable. The main difference is the type is on the right. The name of the variable is on the left. So yeah, the semantic types is this idea. So let's say we have a person, and it's a fairly simple person. He has a first name and the last name. Come on. Okay. So yeah, as I mentioned, we have a person, and his first name is John, and then it's Smith, and then who sees the error? Can you raise your hand? That is horrible. It's like 5% of the room. So the error is that we assign the last name to the first name to the last name. And it's a fairly common thing to accidentally mix up some parameters. It's a very human thing. It's a very stupid thing, but things like this happen. And sometimes they slip through the tests. And it might be a very hard thing to catch. So the idea is that we introduce extra types. We just introduce two new types, with first name and last name, and they just wrap a string. Now, when you type this, we introduce types. I have highlighting here. And instead of just using raw strings, now we use these new types that we defined. And in Coming back. And instead of, assigning directly, we do this, which still can be, you can still make an error, but it's a lot easier to see. Like if I wrote first name equals last name, that's a bit easier to see. It's very explicit and in your face. And then if you do, if you do mix up these two things, you're gonna get a compiler error because the types do not match. So it's a very simple idea, but it can save you. And one of the ideas is that maybe in the project, you shouldn't even ever use a raw type instead of, a semantic type ever. So the only place where you should use the raw type is if you, are defining a semantic type. It's a kind of an extreme idea, but it's worth thinking about. So you can, with semantic types, you can attach semantic meaning to raw types, like string and integer. We can document the meaning once on the type itself, instead of all over the place. The compiler can tell us if we mixed up the arguments. We can restrict the values of that type. So, often there's string, but it's not any string. It has to be in a special format. So who enforces that? Most of the time, nothing. Here, we can enforce that notion using either runtime-based or macro-based smart constructors. I'm gonna tell what that is. And we can actually define a valid set of operations between types. Like, you can multiply the volts with amperes and you will get watts, if I remember my physics course correctly. So yeah, so for example, we have a string called email. And we can make the constructor private, so not anyone can construct it. And we can create like a smart constructor, which basically just does validation. So you give it a string and it says, if the validation passes, then it's gonna be an email, right? We're gonna construct it. But if it fails, then we're just gonna have an error. And this is a type that says it's gonna either be an error or an email. Well, yeah, you should probably have an error as well here. But the idea is, because this is immutable, once you have email value, it is validated because there is no way for it to be constructed in a way that, it's invalid. And regarding the operations, so we have volts, we have amperes, and we can define what multiplication means. And, instead of just having everything as a double. And there's a fun fact. So NASA actually once blew up a rocket, like a spacecraft, because they multiplied miles with kilometers. There's a link here if you want to read about it. It's horrible. But yeah, there was a part of the team that worked in UK and a part of the team that worked in USA. And, one country uses kilometers, the C system, and both teams were from USA. Oh, God. Well, yeah, humans are humans. Something happened. They got the units mixed up. Very expensive mistake. Could have easily avoided it. Another thing that we can do is use union, or also known as sum types. So it's also a fairly easy and simple idea. You just basically say, this type can have 1 out of 5 values. So we can do that with C# and enum enumerations, but this allows you to add extra data to those enumerations. So some languages support it natively, like Scala, F#, Rust, Kotlin. Some languages need extensions or linters, like C#. So there's this thing, and Once you have it, you can do this. You can define that I'm gonna make this interface into a closed interface. Here's all of the variants that are there. And then, you just write down, here's one variant with this data, and then there's another variant with this data. And then once you have it, you can do an exhaustive switch. So basically you say, if it doesn't, you check one case, another case, and if it's none of those, you say exhaustive match fail. So what this essentially does is, by using that compiler Roslyn analyzer, it analyzes this at the compile time, and if you manage to not check any of the cases that are listed here, it will be a compile time error, which is very nice, because when eventually you will come and add a new mode, instead of you trying to hunt down all of the places where that should be handled, the compiler will just tell you and will refuse to compile your code until you fixed all of the places. Proof values. So this is also another very simple idea, but very useful one. So sometimes we do have side effects and functions that do not really do anything except side effects. They do not compute anything. And we, if you change the order of two lines together, everything will break. So how do we make sure the compiler can help us with this? So the idea is you just say, there's a proof value. You define a type. You say, movement has been handled proof. It doesn't have any data in it. Nothing here. But the idea is that you have a function that does some side effects, and at the end of it, it just creates this proof value. Well, there's an error. It should be proof. But it creates this proof value. Yeah. And then in the handle shooting method, you accept this value. It doesn't have any data, so it's not very useful, but it's useful in a way that it now enforces ordering. So if you switch these two lines together, the compiler will say you're trying to use a value which does not exist yet, therefore compilation error. Of course, you can always circumvent this by just creating a proof yourself, but then you're just doing malicious code, and nothing's gonna save you from that. Path-dependent types. So this is actually a thing that needs to be supported by a language, like C# does not support that, and it allows you to bind specific values to specific instances, and it's useful with immutable data structures. So let's presume we have this, let's presume that we have this thing called a safe vector, and it's just basically a collection, an immutable collection of elements of type A. What we can do here is we can define, so this is Scala, we can define a type called index inside of the vector. And we can say that we have this operation index by, and you give it a predicate and it's gonna return an option of index. And then you have the standard get by index operation, which says, you might give me the wrong index. Therefore, I have to return an option because, there might not be an element there. And you have another get by index operation, but this time you know that the index is the correct index, and therefore you can always safely return a value. So how does this work in practice? Let's try to misuse it. So we have two vectors, both of them are safe vectors. Where do I point this? We search for the, element. We search for a string that is of length of 5 in the first vector, and maybe we find it, maybe we don't. This is an option. But then, if we do, we get an index here, and we try to use that index on the value on the second vector. And because the index type is defined inside of another type called safe, safe vector, the compiler will tell us, oh, what you're doing. I expected to find a value of type vector2 index, but I found a value of type vector1 index. So this is a way to make sure you can eliminate a certain class of errors, like index out of bounds error. The trick is that this thing needs to be immutable because, you get some proof here by performing an operation, but if this thing is mutable, then you can mutate the thing and your proof will possibly become invalid. So if it is immutable, then you can safely provide the get operation, which knows that it cannot fail anymore. Constraint types. So it's similar to semantic types, but it provides knowledge about the structure of the data instead of the semantic meaning. So for example, we can define things like non-empty. So this thing A is non-empty. It might be a non-empty string. It might be a non-empty collection. Or maybe even, like it's a collection which has even amount of elements and other predicates like this. And when we know the structure, we can say certain elements, certain operations are always 100% safe. Like if we have a non-empty collection, it's obvious that we can always take a random value as safely, and the first value as safely, and the last value as safely. So, and reduce is always safe. So you can define a different API for things that that are non-empty. It's problematic because the types can, if you implement it using generics, the types can get complex and non-compatible. So for example, if you have non-empty vector that has an even number of elements, and then you change the order of these things, suddenly the types for the compiler are different. So that's bad. But this all depends on the encoding that your language supports. So in Scala, you might have a different type of encoding, not using generics, but using union types. And you can say, this is a vector with these traits, with these tags. It's a vector with non-empty tag and an even tag. And then the order doesn't matter. And a lot of this is basically about thinking in type signatures and making sure that your type signatures are proper and do not lie. So a lot of information can be put into a type signature, and you can learn a lot about what the function does from the type signature. So for example, if we say it's a function that splits in half a vector, that can potentially fail because the vector can be of an odd size, and then you can't split it in half because the halves will not be of an equal value, of an equal size. But if we know that this thing is a vector which is tagged with even, then we know that it's not an either, and we can always split it in half because it's even. So yeah, what are the conclusions from this? Basically what you can, take from this and apply to your project depends on what kind of language are you using. If you're using a dynamic language, you're gonna not apply any of this, basically, but the more capabilities your language has, the more advanced type system it has, the more information you can encode into that type system, And instead of you writing tests to test for it, you can use the compiler to kind of prove those things in the type system when it's compiling code. And then you can remove, tests. If you can make it easier for everyone to understand your code, and then you can kind of make it less error prone to refactor stuff. You can just move things around and rely on the compiler to tell you where you are wrong. This is just some tools you might enjoy. So there's refinement types for Scala. If you're using Scala, very useful library. You can take basically any type. You can say, this is a number between 5 and 25, and define that as a type. There's also this library called Shapeless, which allows you to use generic programming to define various things. I'm not going to go into there. It's another topic. For the C#, you can use the exhaustive matcher. And we also have written our own, we took Roslyn and we kind of extended it and we added stuff to it, most notably macros and records and implicit resolution, which are features from Scala that we very much liked and added. So this is in a very rough state, but if you're interested in this, you can reach out to me and I can introduce you to stuff. And maybe we can actually build a community around this thing or something. That's it. Questions and answers.
We have one from stream. How close is this with functional programming?
So the question is, how close is this with functional programming? Yeah, so the idea of functional programming is of immutable values, as you've seen, for example, with path-dependent types. They are most useful with immutable stuff. In fact, this whole thing meshes with functional programming very well, and is probably enhanced if you're using functional programming paradigm, because it all relies on the immutability of stuff often. But it's not, I wouldn't say it's, very much dependent. Like a thing like a semantic type you could use on any type of programming paradigm. The question is, if you use these types extensively, is the compile time something you need to worry about? It depends. Usually no, but you can go, like with C#, it's probably not the problem. Like we haven't experienced it. With Scala, you can go into very advanced type trickery, which will blow your compile times through the roof, and then you go and profile the compilation. With compilation profilation tools. So, everything has a downside. But it's most of the time, no. How do juniors react to this kind of techniques? Well, the same way as juniors do to everything. They're very scared. But, they get along fairly quickly, like it's not rocket science. So for union types in C#, you can use that exhaustive matching Roslyn plugin that somebody wrote, and that's pretty much how it works, and it works pretty good. It provides exhaustive matching for enums, and it also provides exhaustive matching for type hierarchies. How do you handle null checking? Well, you don't use nulls. If you want to represent nullability, like the possibility of something being absent, you just use the proper type of that, and that type is usually called option or maybe. And it's just a fairly simple thing. Actually, C# has an option type. It's called system.nullable, but for some reason it is constrained for structures only. So if you just remove that constraint, you pretty much get an option type.
So that's about it. Thank you, Artur.